Good morning, students. Today's lecture focuses on bactiofugation, an advanced centrifugal separation process used for microbiological quality improvement in milk. Unlike clarification, which removes visible dirt, bactiofugation specifically targets bacterial spores. In this session, we will examine the principle, construction, working, efficiency, applications, and limitations of this process. Let us begin with the basic concept of bactiofugation. Bactiofugation is a specialized centrifugal process designed to remove microorganisms, particularly bacterial spores, from milk. It operates on density difference using high centrifugal force. The equipment is a modified disc stack centrifuge called a bactofuge. Since spores are heavier than milk plasma, they move outward toward the periphery while clean milk flows inward. Why do we need bactiofugation? Standard pasteurization at 72 degrees Celsius for 15 seconds cannot destroy heat-resistant spores, especially Bacillus and Clostridium species. These spores can cause late-blowing defect in cheeses such as Gouda and Emmental. Psychotrophic spore formers also reduce shelf life of pasteurized milk. Therefore, physical removal of spores improves microbial quality without excessive heat treatment. The principle of bactiofugation is based on Stokes' law and density differential. Sedimentation velocity depends on particle diameter squared, density difference, centrifugal acceleration, and viscosity. Spores have density around 1.30 gram per centimeter cube, while milk plasma is approximately 1.03 gram per centimeter cube. Since the density term is positive, spores move outward toward the bowl periphery under high G force. This density difference is the foundation of separation. Let us examine the construction of a bactiofuge. The key component is the disc stack assembly. Conical discs increase surface area and reduce sedimentation distance. A hermetic bowl prevents contamination. Sludge space collects heavy spore sludge. Discharge mechanism allows intermittent ejection of concentrated spore sludge. CIP capability enables cleaning in place without dismantling equipment. Thus, the system is compact and hygienic. Now we study the working of the bactiofugation system. Step 1. Preheating. Milk is heated to 55 to 60 degrees Celsius to reduce viscosity and improve efficiency. Step 2. Inlet and spin. Milk enters the hermetic bowl and spreads through disc channels. Step 3. Separation. High centrifugal force separates heavy spores from lighter milk. Step 4. Discharge. Heavy phase exits through peripheral outlet. Light phase, the bactiofugated milk, flows from the center outlet. This is a continuous separation process. Removal efficiency is significant. Anaerobic spores, approximately 98% removal efficiency. Aerobic spores, around 95% removal. Lactobacilli and general bacteria, approximately 93% reduction. This high removal rate greatly improves microbiological quality before pasteurization. The microbiological basis of separation depends on density and size factors. Milk plasma density is about 1.032 gram per centimeter cube. Vegetative bacteria density is around 1.07 gram per centimeter cube. Bacterial spores have density near 1.30 gram per centimeter cube. Particle size of spores ranges from 0.5 to 2.0 micrometers. Centrifugal force applied is typically 5000 to 10,000 G. Process temperature of 55 to 60 degrees Celsius reduces viscosity, enhancing separation speed. Let us compare clarification and bactiofugation. Clarification removes visible dirt, somatic cells, and large impurities. It operates at lower centrifugal force, around 4000 to 6000 G. Bactiofugation removes invisible microorganisms, especially bacterial spores. It requires higher centrifugal force, around 8000 to 10,000 G. Clarifier sludge contains dirt and cells. Bactiofuge sludge contains concentrated spores, critical for food safety. Thus, the purpose differs significantly. Advantages of bacteriofugation include efficient spore removal, reducing heat-resistant Bacillus and Clostridium, flavor preservation since ultra-high heat treatment is not required, improved cheese quality, preventing late-blowing defects, extended shelf life of market milk, especially ESL milk, reducing initial spore count. Therefore, it works synergistically with pasteurization. However, limitations must be considered. High economic cost due to high-speed operation and capital investment. Loss of solids. As bactofuge sludge contains milk proteins, it must be sterilized and reprocessed to avoid economic loss. Pre-clarification is required to prevent excessive sludge buildup. Discharge challenges, as intermittent discharge may cause pressure fluctuations. Thus, process optimization is necessary. Applications in dairy industry are extensive. Cheese production, especially Gouda, Emmental and Swiss varieties. Whey processing for high protein concentrates requiring strict microbiological standards. ESL market milk, reducing initial spore count for extended refrigerated shelf life. Low heat milk powders where thermophilic spore reduction is essential. Hence, bacteriofugation enhances product safety. The process flow summary is as follows. Raw milk receiving, to preheating 55 to 60 degrees Celsius, to clarification and standardization, to bacteriofugation, to pasteurization 72 degrees Celsius for 15 seconds, to rapid cooling below 4 degrees Celsius, to storage and packaging. Bacteriofugation is positioned before pasteurization to reduce microbial load prior to heat treatment. To conclude, bacteriofugation is an advanced centrifugal process used to remove bacterial spores from milk. It operates on density differential under high centrifugal force. It improves shelf life, cheese quality, and microbiological safety without excessive heat treatment. However, economic and operational considerations must be carefully managed. Thank you.